particular example, we've been asked to graph the rational function y equals x divided by x squared minus 9. Now, I've factored the denominator in this case so that our function can now be expressed as y equals x divided by x plus 3 times x minus 3. The reason why I factored the denominator is so that I can see the vertical asymptotes and also discover the restrictions in the domain. So the first part of the question is to state the domain. As you know, you cannot divide by 0, so therefore x cannot be equal to 3 or negative 3 for this particular function. You could write that in set notation, but I've written it in interval notation, so my domain is that my x values go from negative infinity to negative 3 in union with negative 3 to 3 in union with 3 to infinity. Because squared brackets haven't been used with the negative 3 or the 3, we're not including those particular values in the domain. My x-intercept and y-intercept are exactly the same in this particular case. The y-intercept would be found by setting x equal to 0, and you would indeed get an answer of 0. The x-intercept would be found by setting y equal to 0 and solving for x. In the case of a rational function, you should be aware that all you have to do is set the numerator equal to 0, and therefore the overall expression will be equal to 0, and that will occur when an x value of 0 is used. The only exception to that rule is if you end up with an indeterminate form where you end up with 0 divided by 0, but that's only occurs on rare occasions. So we have our domain and our x-intercept and our y-intercept. The next thing we have to determine is the function odd, even, or neither. To be even, f of x has to equal f of negative x. So that's what I start by doing, finding the f of negative x. So every place in our function where we had an x, we replace it with a negative x. And we discovered that the f of negative x is equal to negative x divided by x squared minus 9. You can see that that's not equal to our original function f of x. So this function is not even. Well, if the function is odd, the f of x has to equal negative f of negative x. So we take our f of negative x that we just worked out and we multiply it by a negative 1. So negative f of negative x is equal to negative 1 times negative x divided by x squared minus 9. When I do that, I get x divided by x squared minus 9. So in this case, f of x is indeed equal to negative f of negative x. Therefore, the function is odd. The next thing we have to do is determine if any asymptotes occur. This requires that you think back to what you learned in pre-calculus regarding rational functions. You know that vertical asymptotes occur when the denominator is set equal to 0, and that will occur when x is equal to 3 or x is equal to negative 3 for this particular function. So there are two vertical asymptotes. The horizontal asymptote in this particular case will be y equals 0. The reason for that is that the numerator is of lower degree, because it's a linear expression, than the denominator, which is a quadratic expression. So when the numerator is of lower degree than the denominator, then my horizontal asymptote is at y equals 0. Now, you may be scratching your head a little bit and saying, wait a second, I've got a horizontal asymptote at y equals 0, yet my function has a y-intercept and x-intercept at 0, 0. How can my function be crossing my horizontal asymptote? Again, you have to go back and think about what you learned in pre-calculus. And we realized that this little shortcut that we use for calculating horizontal asymptotes actually relies on a limit as x approaches infinity and x approaches negative infinity. Therefore, a function in or around the origin may indeed cross the horizontal asymptote, because we're not looking at x values that are approaching infinity or negative infinity in that particular case. On the next screen, what we've started to do is try to determine if we have any extrema for this particular function, whether we have any minima or maxima. So we determine that by taking the derivative, y prime, and in this case we're forced to use the quotient rule to do so. We want to take that particular derivative and we want to set it equal to 0. So we end up with 0 is equal to negative x squared minus 9 divided by x squared minus 9, where that denominator is all squared. In order to set that particular expression equal to 0, really all we have to do is set the numerator equal to 0. So 0 is equal to negative x squared minus 9. And if you used your quadratic formula, you would find that there are no real roots to this. Therefore, there are no extrema for this function. That doesn't mean that the function is either solely increasing or decreasing. Remember that around vertical asymptotes, on either side of it I should say, a function can change from increasing to decreasing or vice versa, or it may not change at all. So when we're trying to determine increasing and decreasing intervals, we not only look at extrema that we may have calculated, but we also have to consider vertical asymptotes because, as I just mentioned, the function can indeed change from increasing to decreasing or vice versa across those vertical asymptotes. So I've put down a number line, and I have no extrema to write on this number line, but I do have the two vertical asymptotes. So I put down the negative 3 and the positive 3, and that shows me that I have 3 intervals that I have to test. So I'm going to test y prime, and y prime was the negative x squared minus 9 divided by x squared minus 9, all squared in the denominator. So I'm going to test y prime at x equals negative 4, x equals 0, and x equals 4. Those are the values that I chose in my 3 intervals. Again, you could have chosen any values you wished. When I took the x value of negative 4 and substituted into my first derivative, I got the value negative 0.51. So I place a negative on my number line. That indicates that my function is decreasing from negative infinity to negative 3. Then I took the x value 0, substituted it into y prime, my first derivative, and got negative 0.11. So my function is decreasing from negative 3 to positive 3. And then I substituted the x value of 4 into my first derivative, y prime, and obtained negative 0.51. Another negative value, so I know my function is decreasing from 3 to infinity. So I do not have any increasing intervals at all for this particular function, so I say for increasing, my x values are a member of an empty set. Well, now I have to determine if I have any points of inflection. Points of inflection occur when our second derivative is equal to 0 or our second derivative is undefined. There's also the additional criteria that the concavity has to change across that particular point in order that it be classified as a point of inflection. But we'll deal with that later on. So, to find my second derivative, y double prime, I have to use the quotient rule, and embedded within that quotient rule is the chain rule. So it's quite a cumbersome question. And so I end up with y double prime is equal to x squared minus 9 all squared times negative 2x subtract negative x squared minus 9 times 2 times x squared minus 9 times 2x. And that's all divided by x squared minus 9 squared, which is then squared. Now, I've deliberately made a mistake on my next step, so please don't copy it down. What I've done is I've just merely gone ahead and just expanded all the terms in the numerator. And what you'll notice is that eventually I'd be left with a fifth degree polynomial in the numerator, which I'd be setting equal to 0 and attempting to solve. That is really problematic. So if you remember when we first learned the quotient rule as well as the product rule, we spent a lot of time looking at how the expression could be simplified by common factoring. And that's the mistake that I made in this second step on this particular screen. I didn't try common factoring. So what I'm going to do is erase what I have, and I'm now going to consider that I can common factor with those terms in the numerator. From both of those expressions, separated by the subtraction sign, I can common factor out a 2x and an x squared minus 9. And when I do that, that leaves me with a negative bracket x squared minus 9, close the bracket, subtract 2 times negative x squared minus 9, closing the brackets again. And then that's all divided by x squared minus 9 to the 4. Well, what you'll notice is that I have an x squared minus 9 to the 1 in the numerator and an x squared minus 9 to the 4 in the denominator. So a little division can occur here. And also with the terms in the squared brackets, I can expand them and combine the like terms. So my third step on this screen reads as 0 equals 2x times negative x squared plus 9 plus 2x squared plus 18. And that's all divided by x squared minus 9, where the x squared minus 9 is all raised to the 3. Combining my like terms, I get 0 is equal to 2x times x squared plus 27, all divided by x squared minus 9, all raised to the 3. I'm trying to set this expression equal to 0, so really all I'm concerned with is setting the numerator equal to 0. So either the 2x equals 0, which gives me an answer of x equals 0, or my x squared plus 27 is equal to 0. And when I attempt to use my quadratic formula here, you'll find that you have no real roots. Actually, you don't even need to use the quadratic formula. You would discover that x equals plus or minus the square root of negative 27, and therefore there's no real roots for that particular case. So when x is equal to 0, we need to find the corresponding y coordinate, which is 0 when you substitute it back into our original rational function that we were dealing with. What you'll notice is we've seen the point 0, 0 before. That's our x-intercept and y-intercept for a particular function. So it may possibly also be a point of inflection. We'll have to test concavity on either side of that to confirm that. Now, even though we only have one potential point of inflection, which would occur at an x value of 0, you'll notice that on this particular number line I've included negative 3 and positive 3. If you remember, those are our vertical asymptotes. And just as a function can change from increasing to decreasing on either side of a vertical asymptote, the same is true with concavity. So we have to put those particular values on our number line and test all the regions created using both those vertical asymptotes as well as the potential point of inflection that we calculated on the previous screen. So we're going to test y double prime, second derivative, at these particular x values. X equals negative 4, x equals negative 1, x equals 1, and x equals 4. If you can't remember, y double prime in this case is equal to 2x times x squared plus 27, all divided by x squared minus 9, which is all cubed. The x squared minus 9 is. So I substitute in my x values into my second derivative. When I substitute in negative 4 for x into y double prime, I get negative 1.00. So I know my function is concave downwards from negative infinity to negative 3. When I substitute x equals negative 1 into my second derivative, I get an answer of 0.11, a positive value. Therefore, I know the function is concave upwards from negative 3 to 0. When I substitute x equals 1 into y double prime, I get negative 0.11. So I know my function is concave downwards from 0 to 3. And then when I substitute in my last x value, x equals 4, into my second derivative, y double prime, I end up with 1.00. So I know my function is concave upwards from 3 to infinity. So to recap, my function is concave upwards from -3 to 0 in union with 3 to infinity, and it is concave downwards from -infinity to -3 in union with 0 to 3. Now what we have to do is take all this information and put it together and draw our sketch of our curve. As I mentioned with the previous example that we did the other day, it's probably best to plot this pertinent information as you go rather than leaving it till the very end and trying to figure out how everything pieces together. The reason for that is you often make a little careless mistake on your previous steps, and if you're plotting the information as you go, it's much easier to catch those mistakes before they get out of hand. Well, what I started by doing is plotting my x-intercept, y-intercept for this particular function, which is at 0, 0. The next thing I'm going to do is plot on the asymptotes that we have. We have a vertical asymptote at x equals 3 and a vertical asymptote at x equals -3, and we have our horizontal asymptote at y equals 0. I've plotted these with the green marker and used little dotted lines to represent them. Now, other than this, we really don't have a lot of other information to go on. If you notice when you go through the work that we've done previously, there aren't a lot of points. The only point we have for this particular curve is 0, 0, which not only is an x-intercept and y-intercept, we later learn that it is also a point of inflection. But how do we put all this information together so that we can actually draw a curve, even though we have so few points? Well, let's ask ourselves about the increasing and decreasing regions for this particular curve. We know that the function is decreasing from -infinity to -3. So what I've done with the green marker is just drawn in a line. It's not the actual line that I want to use, but I'm trying to indicate where the function is decreasing. You'll notice that I put it below the horizontal asymptote because that was the only thing that made sense in terms of the function adhering to both the horizontal and vertical asymptotes in that region while still being decreasing. I then continued over, and I know that between -3 and +3 the function is decreasing. So again, taking into account the horizontal and vertical asymptotes, using the green marker, I've drawn in two little straight lines to indicate where I believe the curve is going. I haven't considered concavity at this point, but I'm just trying to get a handle on what information I have up to this point. And then I also know that the function is decreasing from 3 to infinity. So again, taking into account where my horizontal and vertical asymptotes are in that region, I've placed my little straight line, which is decreasing in this case, just above the x-axis or the horizontal asymptote, because that's the only way it can be configured such that the curve follows those two asymptotes. The last thing I'm going to consider is now the concavity. Well, from -infinity to -3, the curve is supposed to be concave downwards. So I've drawn in with the blue marker what I believe the curve should be doing. Then from -3 to 0, the curve is supposed to be concave upwards. So I've drawn that portion in. And then from 0 to 3, it's supposed to be concave downwards. And finally, from 3 to infinity, it's supposed to be concave upwards. So I've now drawn in all that information. And if you take a look, those little green lines that serve as references for increasing and decreasing, they've indeed helped me decide on the behavior of the curve in these regions. I'm now going to erase those because they're not actually part of my final answer. Now, the only thing we should probably go back and consider is a couple of points that we had overlooked. If you remember earlier, we said that the function was odd, meaning the f of x equals negative f of negative x. Well, another way of describing an odd function is that it has 180-degree rotational symmetry about the origin. And when you look at this particular sketch that we've drawn, sure enough, it has that symmetry as described. We'll also notice that our point of inflection at 0, 0 seems to be adhering to all the rules. The curve is indeed changing in concavity when we cross that point from left to right. It was just to the left of the point, it's concave upwards, just to the right of the point, it's concave downwards. So that indeed appears to be a point of inflection. So we now have the completed sketch of this curve. Remember, anytime I ask you to do one of these particular questions, I will be asking you to show all your work. I realize that you have a graphics calculator right next to you and that you can find many of these answers just by accessing some of the menus on the calculator. That's why I insist that you show me all your work.